A very quick review of our previous lectures. I hope we still remember some of the key conclusions, right? So I think the main point of last lecture is many electron wave functions. So it's very unique. It's very different from the single electron wave function that we have been used to for a long time. Right? We have been talking about orbitals all the time, but more practically, what we really deal with is the many electron system, and they have their own uniqueness. And some of the keywords I want to remind of everybody here is, first, the wave function needs to be asymmetric, right? Because the electron, in essence, is a fermion. So there's a very fundamental requirement about its wave function. It must be asymmetric. And that would have a lot of consequences on what kind of form the wave function can be, and what kind of some unique quantum mechanical phenomenon that we can have. For example, the exchange energy, and we'll mention that again in the next slide. And the third one is I put this kind of a question here. I think this is something that there have been commonly used when we discuss the electronic structure, right? We are used to drawing the electron occupation diagram, and there is being a common practice to associate this kind of occupation diagram with the implied wave functions. In some cases, they have direct correspondence, but not always, right? So last time we mentioned that our configuration or electron occupation diagram does not necessarily mean it's a valid wave function, because sometimes it doesn't really satisfy the asymmetry requirement. And we gave the example of excited helium, which probably is the most simple and practical many electron system. It have their 1s electron and also a 2s electron. And we went through some of the mathematical details, and there we saw that actually we can identify in two kind of states. One is a singlet, and the singlet is in fact is not either of those four possible configurations, but instead is actually a linear combination of these two configurations, right? Because if we only use this one, it doesn't satisfy the asymmetry requirement for the wave function. So we have to construct a linear combination. And for the singlet, it's actually a subtraction, and it is addition then turn out to be part of the triplet. So the triplet includes this kind of two states, which are easy to configure since they're parallel spin, and we can appreciate that they have a lower energy. But this one may not be very straightforward. And this is a linear combination of the two possible configurations. And this satisfies the asymmetry requirement for the wave function. Okay. So another point is about exchange energy. And this still originates from the requirement on asymmetry. So the asymmetry requirement for the wave function of electrons, in fact, leads us to construct a linear combination of possible configurations. And that's how the linear combination of configurations arise. And once we plug in those kind of forms of those kind of constructed wave functions into the Schrodinger equation to calculate the energy, then we will see actually this kind of exchange energy term would arise. So we can see this exchange energy has a pure quantum mechanical origin, right? It simply has no classical analog, for understanding this. And also, we cover this important conclusion about the energy of many electron system. It should typically include a non-interacting energy, as though their electrons, they're neglecting each other. They're simply interacting with the nucleus, and also the interaction part involving the interaction among electrons. And that includes both the Coulombic interactions and also its exchange interactions. So without going too much mathematical details, I think we should at least memorize this kind of term and know what kind of energies are involved for a many electron system. Okay, so that's pretty much the quick review. And now let's move forward to the main topic we want to discuss today, the atomic term symbol. And at the very beginning, I want to show the relevance to what we studied, right? We studied transition metal oxides all the time. We collected transition metal LH all the time. And we see some kind of a spectrum, which is typical like this, right? And I still remember Dean asked this kind of question in the last lecture about, how we can understand the main electron for the transition metal oxides. So that's something we will want to discuss in this lecture and in the following lectures. And looking at this kind of spectrum, I don't know about you, but I probably would, naturally ask this kind of questions. Why we have this kind of two sets of peaks, right? And typically we say this is L3, this is L2. Why there's two sets? Because it seems that we're only generating a one hole, right? We have only one hole, and then we have we can understand that the excited electron may occupy different d orbitals, but we have only one hole. Then why we have two sets? So this is the first question, and we'll answer that. And the second thing is why there are so many peaks. So this is you probably will say this, okay, this is 1, 2, 3, 4, maybe some shorter peaks, not too many, but those are the peaks that have already broadened by the instrument broadening and also their core lifetime broadening. So these are broadened peaks. If we have a very fine instrument, let's say the best instrument in the world that can really resolve all the peaks, we would in fact observe a lot of peaks corresponding this kind of the spikes. And in fact, this is not a very seemingly complicated system. It's only, let's say it's a 3D 3D3 or 3D4. So if we think about the picture of the crystal field splitting, then we may think, okay, there's only T2G and EG, right? So there's only correspondence over exciting electron from 2p either to the T2G or to the EG. Then why we would get so many peaks? So this is the second question we want to answer. And that closely relates to the topic we want to discuss. And thirdly is very practically important. After knowing all this stuff, can we predict or calculate this kind of a spectrum? And what kind of information we can get from analyzing this kind of spectrum? So I think that practically relates to our research. So when we look at a transition metal oxide spectrum like this, what kind of information we can get? There are some, practices in the literature, for example, analyzing the L3 to L2 ratio, right? Analyzing some of the peaks. Can we do more? So those are the questions that I keep in mind when I prepare these slides. And also, hopefully, after we go through all the lectures, we can answer all of them. So what is a term symbol? A term symbol is something like this. So you will see a number here, but in fact, it's the physical meaning corresponds to total spin number. So that's S, corresponds to S. And this is L, we naturally associate L with the orbital angular momentum, right? So we have the L number, and in the language of a spectroscopy, this appears not as a number, but as a symbol. We'll talk about that later. And this is a J. J can be regarded as a total angular momentum, because we know the electron has on one aspect, it has the orbital angular momentum, right? It also has the spin angular momentum. So imagine that we're sitting on a rotating table, but at the same time we can also have the freedom to rotate ourselves. Sort of a picture like the Earth orbiting around the sun. The Earth itself is also rotating. sort of an analog, but we know it's classical picture, and quantum mechanics is based on the wave function, and there's no we have to describe them using waves, but we can draw an analogy to help us to understand. So T is the total angular momentum. So this is the term symbol, and we may ask why this is useful, right? Looks very simple, owning 3 items, and why we want to spend so much time studying it, understanding it. What's the benefit? So why is it so important? I tried to capture the essence of term symbol in my own language, but in case I realize it's not comprehensive, I'll update this expression later. But at this point, I would say term symbol is so powerful because it can directly tell us the energy level without solving the Schrodinger equation for many electrons. I think one of the impression we had from our last lecture might be that, many electron wave function is complicated, right? We have to do a lot of things, go through a lot of integral, a lot of calculus to get something that is, even only approximation. It's complicated. And that's why term symbol is so powerful. Term symbol is saying, we don't have to really solve this Schrodinger equation. We don't really have to get the exact form of their wave functions, but directly through some derivation, which is not complicated, is based on a very simple algebra, we can derive the term symbol and tells us the energy levels of the possible wave functions. That is powerful, right? And that has the direct correlation with the spectroscopy, because we know in spectroscopy, we are basically exciting electrons. So we are exciting them to some excited states. And what we really see, in fact, are only their energy differences. We always see the energy difference between the excited states and the ground state, right? So in other words, if we know how many term symbols are involved, then we immediately know how many energy levels are involved. And then we know how many peaks there would be in the spectrum that we observe. They can be obscured by their instrument broadening or the cohort lifetime broadening, but yeah, we'll get to the ballpark. But before we do more discussion, I also want to explain a little bit about why it can be so cool, right? And also important, why it's so useful. And here, I still want to emphasize the importance of linear algebra. So I already talked about there is importance, I think, in one of the previous lectures. And I think I said that basically quantum mechanics is all about linear algebra. We're basically trying to understand the wave function in a function space. So never underestimate linear algebra. And here I'm listing some of the correspondence between linear algebra and the quantum mechanics. So for linear algebra, we have the operator, right? And we have, in the context of quantum mechanics, we have the operator that is closely related to the physical meaning. For example, we have the Hamiltonian that includes both the potential and the kinetic energy of the electrons of the whole system. And if we calculate based on the Hamiltonian operator, we get to the energy. So that's something we're very interested in. And also we have the orbital angular momentum operator and the spin angular momentum operator and the total angular moment operator and the projected total angular momentum operator. All these operators, they're important because they relate to something physical that can be measured. So for this one is energy. For this one is the orbital angular momentum, and for this one is the spin momentum. So those things can be directly measured, and those things are either the direct eigenvalues of the function or they're some of the key parameters for the eigenfunction. Okay, so eigenfunction in linear algebra, we know a lot of times is basically eigenfunction problem, so that we have an operator acting on a series of eigenfunctions. And by eigenfunction, we mean that if the operator acts on this eigenfunction, then this eigenfunction actually remains, and only that we have a linear coefficient in front of it. So we can go back to the definition of eigenfunction if some memories are getting loose. And in the context of quantum mechanics, eigenfunctions are in fact wave functions. And that's what we need to know. The wave functions are what are mathematical description of the electrons. So we spend so much time talking about wave functions of a single electron and many electrons. So after all, we want to understand the wave functions. And the eigenvalues. So the eigenvalues is simply the coefficient in front of eigenfunction in our eigenfunction problem. And in the context of quantum mechanics, we have a correspondence of corresponding energy, right? So energy is in front of the wave function in the Schrodinger equation. Schrodinger equation is basically saying if we have the Hamiltonian operating on the wave function, what we get is actually the wave function multiplied by the energy. So that's the power of Schrodinger equation. And also we can get the angular momentum and also the spin, some physical measurable quantities. But this one, it may not be obvious, but it is very, very important and is closely related to why term symbol can be so powerful. And we have to memorize this. This is the commutative operators. Maybe you are already familiar with this or have heard of this. In case you haven't, I just want to talk a little bit about what this means. So this simply means if we have a two operator, for example, in the quantum mechanics, we have this Hamiltonian operator and the orbital angular operator, right? So if we have the orbital angular momentum operator acts on the wave function first, followed by the Hamiltonian, it will have the same effect of switching the sequence. If we have the Hamiltonian acted first and then applied the orbital angular momentum operator, we get same results. So if this total part is acting on a psi or wave function, it will have same effect as this part acting on a wave function. So this may be trivial, right? Especially if we only associate this with some multiplication, because we know multiplication is a commutative, and A multiplies B equals B multiplies A. So we say that commutative. But for operators, they have a significant amount of meaning if they're commutative. Commutative operators means these two set of operators, they share the same set of eigenfunctions. So I want to say it again. If two operators that are commutative, then they share the same set of eigenfunctions. And this is very powerful. We'll see why. And the second part is in associating or deriving the atomic term symbol. In fact, we're utilizing this kind of a correlation. The intrinsic correlation is there's a correlation between angular momentum and the energy. So this angular momentum can be either the spin angular momentum or the orbital angular momentum or the total angular momentum. And there's a correlation among them. For example, if the two states, they have a different angular momentum, they would also have different energies. In other words, if we can, sort the levels of angular momentums, if we can find out how many possible angular momentum levels there are, then we know how many possible energies there will be. Right? This is cool because so far we haven't talked anything about solving the Schrodinger equation, but we're already getting the answer to the energy levels. And this is a picture I drew. Hope that to capture the essence of what I mean. So let's say these are the operators we're discussing, right? We have the Hamiltonian, we have the orbital angular operator and also the spin angular momentum operator. They commute, they're commutative, so that they share the same pool of wave functions. And this same pool of wave functions are exactly the wave functions for the many electrons, right? If we want to really find out what they are, we have to go through a lot of challenges. We have to satisfy the asymmetry requirement, and we have to consider the Coulombic repulsion between electrons, makes a lot of approximations. Then we may have the chance of solving what kind of wave functions they are. But if we do not care what they are, we only want to know what are the energy levels. If we only care about this part, then we have a solution. The solution is we can derive these term symbols simply from the total, the operator. That part will be simple, and I'll show in detail. That part is simple, so we can directly derive these atomic term symbols, and we can characterize how many they are. And they will have the one-to-one correspondence between the energy levels. So this is the essence of atomic term symbol. Without solving the Schrodinger equation, getting the exact form of the wave functions, we derived atomic term symbols, and we establish direct correlation between atomic symbol and energy levels. Okay, so this is the key meaning of that. In the respect of the spectroscopic tradition, we know that for the L, in fact, we start from 0, right? If we're talking about a single electron, we have L equals to 0, corresponding to S orbital. We have the p orbital corresponding to L equals 1, and the d L equals 2, and so on, right? And for many electrons, and we also need to derive this L, which is easy to do. And this L would also have some integer number. L starts from 0 and goes all the way up to 4 or 5 or even higher. But instead of naming the term symbol as 0 or 1, 2, as those kind of numbers in the term symbol, we respect the spectroscopic tradition and actually name as S, P, D, F, G. They are not difficult to remember because you can directly tell they still, have the correspondence of one electron picture, right? So for the 0, this is a S orbital. For the 1, this is P orbital. But now we have the capitalized letter of the big S, of big P, and big D. I do not remember all the details, but I think the history was like this. At the very beginning, when spectroscopists, they see some lines, in the spectra, they still have no knowledge or idea about the quantum mechanics. And they have even no knowledge about the Niels Bohr's model of the atom. But what they observe are some of the features of the peaks. So if I remember correctly, I think S stands for sharp. So for S related the peaks, they typically observe very sharp peaks. So that's why that's the origin of S. I think P stands for diffuse. Yeah, for the d orbital involved spectrum, they typically observe some diffuse spectrum. So that's why they call it D. And the F stands for fundamental something. I think I forgot what P stands for, but you can check if you're interested.
A little bit. Principle.
What? I'm sorry?
P stands for
principle, right? Thanks. Yeah, P stands for principle. Yeah. So that's kind of a historic annotation of this terminology. And so in deriving atomic term symbol, we'll actually calculate the total L, the total orbital angular momentum. Then we name it as SPDFG. Okay. Then how to read those term symbols? I think this is also a important part that we need to understand, so that we can communicate people who want to talk in the language of spectroscopy. So for example, for this one, and this is meaning that we have a zero total spin because this number is in fact 2s plus 1. We'll cover that later. And this is the means L equals to 0, right? So for L equals to 0, then we have the S. And this is basically saying the J equals to 1. J is the coupling of both the spin and the orbital angular momentum. And in this case, in J turned out to be 1. And we pronounce this term as a singlet S1. And so you see, the only a little bit, the professional part is this part. So in spectroscopy, we talk about the singlet, doublet, or triplet. So this is a singlet S1. This is the doublet P3, and this is a triplet D1. Okay. And this is a table I simply copy paste from our journal article. It was actually from Frank de Groot. So if you look at the especially transition metal LH literatures by Frank de Groot, you will see a lot of such kind of terminology used in his papers, right? So he's basically discussing the transition for the 2p LH. So we're exciting the 2p electrons, and he's listing the possible the states. And you can see all those states are based on atomic symbol derivation. Right? So there are many of them. And for example, if involved the 3D as a 3D5, in fact, actually we have up to 180 term symbols corresponding to 180 peaks in the spectrum. We do not observe those peaks because they are broadened, right? We'll only observe a set of obvious peaks, but in fact, they correspond to a lot of energy transitions. Okay, so in fact, those are all the slides I prepared. It's kind of too short, maybe a very short lecture today, but maybe also this would be also a good time to reserve some time for discussion if you have questions. Maybe through the interaction we can explain more, if you are still puzzled about some of the points I explained. Okay.
If nobody has any questions, maybe I can start.
Yeah, sure.
So I was just wondering, just for the first question, I'm looking at this table. So the J values for some of these term symbols look like they can be fractional, whereas the S values are not. So I'm trying to understand how the J values add up to be a fractional number, and what could they mean?
Very good point. Yeah. So also a very nice observation. So let's take this one as example, right? So for the J, they can be fractions because J is actually the addition of subtraction between the S, the vector, and the LF vector. We have to follow the vector addition and subtraction rules, so they're not simple numeric, the mass, but we would end up with the fractions. For example, if the S equals to 1/2, that's for the alpha spin, right? We have a spin up, then S, let's say just 1 electron. Then we have the S equals to 1/2. And let's say in this case, the L equals to 1. So that's a p orbital, right? So the interaction between S equals 1/2 and the L equals to 1 would actually lead us to either 3/2 or 1/2. If they're addition, that's a 3/2. And if there's a subtraction, that's 1/2, right? So that's how the J values arise, and they're expressed in the original form of its value, right? So if we see this kind of value, that's the value for J. That means J has this value. But why we always have integers for S? That's a very good question. Because the S, in fact, the value can also be fractions. Let's say, what could be a good example? I think this is a good example. So if you look at this one, you see the S equals 2, right? But in fact, this is already processed value. This is not original S. This is 2S plus 1, meaning that the S, in fact, is actually a 1/2. So this is very likely only 1 electron. So this is 1/2, but we present this in the form of 2S plus 1, because that immediately give us the degeneracy of the states. So we know this is a double states that give us 2 peaks, not two peaks, but 2 states. You know, the degeneracy, they have the same energy. So this is what I mean, right? If we derive the term symbol for this 1s2s, then we get some symbol that has their, their s, the s part equals to 3. That this should be the S3, because we immediately see this is a triplet. But in fact, it's composed of the 3 states, right? And in fact, the total spin equals to 1. This is 1/2, this is 1/2, so they add up to 1. But we express them as 3 because we know this is a triplet degeneracy. That's convenient to read, right?
Yeah, thanks. I had one more question.
Yep.
If nobody had any other. So I was wondering, looking at the transition metal LH that you showed. So usually the LH split into 2 bands, like the L3 and L2. I was trying to understand how the L orbitals separate into 2 different energy levels, to L3 and L2.
Yeah, that's something I promised that we'll be discussing, but apparently I didn't get involved in this lecture. To put it simple, this is basically because once we have a hole, right? In fact, there's a correlation between the spin and orbital, and this is comes from the spin orbital correlation. So if we do not, if we just do not care about quantum mechanics, then we will feel that there's only one hole. But in fact, due to the quantum mechanical effect, the hole actually has, or we can say there's only 1 electron, right? We do not talk about hole. There's only 1 electron in the 2p. And this 1 electron, it has a spin and also has the orbital angular momentum. So they can couple in different ways. So if they couple constructively, then we lead to J equals to 3/2. And if they construct destructively, then will lead to J equals to 1/2, right? So in fact, these 2 set of peaks corresponds to different core hole states. And one core hole state is J equals to 1/2. The other corresponds to 3/2. And also, in fact, that also explains why you see L3 seems to have a larger area, peak area than L2, right? Approximate ratio is 2:1. And that's in fact exactly the ratio between the J equals 3/2 states and the J equals to 1/2 states.
Great, thanks.
Yeah, but your questions are very good.
May I ask a question?
Sure, yeah.
I think I always got the impression is that I think L2 and L3 kind of have similar spectrum shape. However, L1 is very different from them. So I'm wondering, is there a fundamental mechanism or explanation about that?
Yeah, so there we are kind of starting from the basics, right? We're talking about the 1 electron, there are many electron wave function, then we talk about term symbol that can tell us the energy levels.
Mm-hmm.
But the real world is actually still far above. So probably you have heard of Jacob's ladder, right? It's actually some sort of ladder for the quantum chemistry ladder, and defining the complexity that can be involved. And the top level is actually the reality, something we mirror. And the bottom level is probably just some simple approximation. Then we add complexities. And to really understand why they have different waves, then we have to involve more complexities. For example, once there's a 2p hole and 3D coupling, they would redistribute the energy intensities among these two. It sounds complicated, right? It is in fact complicated. So in other words, because those of effects, actually those peaks, they have some mixture. So the L3 in fact have some mixture from L2 part. The peak intensity are kind of redistributed. And for your question about why L2, L3, L2, L1, I think that's mainly relates to once you have the I think L1 is actually the I do not have a very good answer to that, but yeah, I think that's something we observed last time when we were measuring the Aldin, the L edges.
Yes.
So it's very, very good observation indeed. And I think I also need to think about that. Yeah, that's what I have right now.
Yeah, I'm not sure if it's like a universal like observation or it's just a case for the iodide. So I'm just wondering about this. Yeah, thank you.
I think for L1 that involves their 2s, right?
Mm-hmm.
Yeah. So actually for L1, I think one thing it is has high energy because it's starting from 2s, and also because now if we're talking about the spin of the coupling for the 1s, then the situation will be totally different for the 2p, because L2 and 3 there should be from the 2p, right? But if it is the starting point is 1s, then it's different. And also because for 1s there's a singlet.
Yeah.
Right. So because now instead of L equals to 1 for p orbital, now your L is equals to 0. So your spin is 1/2 and your L is to 0. Then no matter their constructive or destructive coupling, you always get a 1/2 for J. Right. So there's only one state for L1 if you start with 1s, but there are two states for L2 and L3 because they start from 2p, right? Because we have L equals to 1. Yes. Yeah, I think that's at least part of the explanation.
Okay, thank you. So that means L1 will be more like KH, those kind of.
Right. It's more, yeah. It's the core hole, the 2s hole interaction with the valence electron will be smaller.
I see. Thank you.
Okay. Any more questions?
So I don't currently have a question, but I do have one comment. So I recall when I was learning this kind of concept in undergrad, I found it very helpful to start with fine structure diagrams, since energy slipping causes different peak position, right? I think it's a very good starting point to help understand the entire model using fine structure. And it's easier to use fine structure to understand different operators and like spin different momentum number too. I just have that suggestion.
I see. So you're saying you had already in touch with this kind of materials in your undergraduate, right?
Yeah, in my undergraduate, I'm from physics department. I have a class dedicated for synchrotron X-ray.
Okay. Let's see. And their spectroscopy is a big part of that.
Well, I think all of it is spectrum.
Okay, I see. Yeah, there are a lot of good resources online. I think the challenge is not finding those resources, but finding appropriate resource that is specific to ourselves, right? Because at a different stage, when we have a different understanding level of this problem, and the materials are sometimes explained in different levels of complexities. So I think we can always make good use of the online resources. And as I mentioned, the MIT, the physical chemistry course is a very good one. Yeah, there's probably a lot of in-depth, but it's very clear, and there are several. So that's my recommendation for that. And also for the transition metal LH, this kind of the whole field has been started by Frank de Groot. I can type his name in case you haven't read his papers. So he's from Netherlands, and he has been doing a lot of work on the transition metal LH. He also has their chemical review paper on their soft X-ray. So that includes both their light element KH, for example, oxygen or fluorine, and also their transition metal LH. So that was a chemical review paper. I think was published there 2 years ago, something. Yeah, and there also, maybe I can say a little bit more words that I think our strategy is not to be, the 1% or 0.1% expert in the field, right? In this field, I think we still regard ourselves as people who studied batteries, and we do the battery research, but we cannot avoid, encounter those there some specific fields now and then. So I would say, let's try to be the top, 10%, right, or maybe 10%, and that could be, that's it. And if we want to really go to even further, that would take a lot of time, efforts, right, and may not be worth it. So that's my view of the general strategy we can take when we try to, to understand or learn some specific skills. Okay. And I apologize for the bad timing, because I thought I can maybe go on for 40 or 50 minutes, something based on the slides, but turned out actually probably only finished in 20 minutes, something, or even shorter. Yeah. So Arthur, do you have questions? I see you're
yeah, sorry, I'm trying to think of how to, I guess, phrase it, but I guess I think maybe it's a little outside of this, but just looking at the LH spectra. So each specific, so if you looked at the calculate, or no, the each identified peak on the bottom, I guess each of those, I guess, corresponds to it would say a different state. But what drives the what drives the different intensity between the peaks? Is it just how long each state lasts, or what? Yeah, what is that?
Degeneracy.
Oh, it's so the okay.
The degeneracy. Yeah, yeah. So for example, this one should be a very small degeneracy, and this one you see that you probably say there, is not multiples of this, right? Because actually there are several states, and they seem to overlap, but actually they have a very close the energy. So because this one have, probably composed of several term symbols, and they can have high degeneracy. Then we observe the peak intensity. And also, yeah, I think that's a good point. That's also one of the motivation we want to learn this, because we want to know where are the peaks and how strong are the peaks, right? It's something kind of universal for their characterization. And in XRD, we ask the same question: where are the peaks, and how strong are the peaks, right? So in X-ray diffraction, we spend a lot of time on talking about the structure factor. So actually, which is the essence of the peak intensity. We want to understand that. And so in spectroscopy, we also need to understand why some are strong and some are weak, right? So one thing relates to the degeneracy. The other thing also relates to the selection rule. So for spectroscopy, we still have to obey the selection rule, right? So for example, if it's LH, then we're exciting from the 2p, then the final state only can be D or S, right? Because this should be the delta L should be equals 1. So there's also the requirements on the selection rule. So some are states that we can never approach because they are forbidden by the dipole selection rule. But if we talk about the hard X-ray, so we still observe some very weak peaks arising from the quadrupole interaction. So most of the time we're talking about the dipole interaction, but there are also quadrupole interaction. Then they will have different selection rule, right? So those are some of the details.
Thank you.